now we're going to do our second problem here. A passenger on a Ferris wheel moves through a distance of 12 meters before it stops to drop off a passenger. If the passenger carts are all 35 meters from the axis of rotation of the Ferris wheel, what angular displacement does each cart move through during this part of the ride? Okay, so if we were to draw a Ferris wheel here, okay, and this is going to be my crude picture, but at the end of each of these spokes is going to be like the little cart where everybody gets on and off the ride, okay? All right, so if you're going to be dropped off, then that means you're right here, okay? Now, it says that the passenger is going to move through a distance of 12 meters before it stops to drop the person off. And if the passenger carts are all 35 meters from the axis of rotation, then that's our radius, right? Here's our axis of rotation, and we're going out to the cart. That's from the center of the circle out to the edge of the circle. So that's going to give us a 35-meter radius. And it tells us that our linear displacement, I guess you could call it, our arc length, okay, is going to be 12 meters. So arc length equals 12 meters. Does that make sense to everybody? We traveled through 12 meters before we got to come to a stop, right? And now we're wondering, what is the angle that we traveled through, right? So right here, we want to know what our angle theta is, okay? So what formula do you think we should use? Probably the arc length formula. Very good. S equals R times theta. And in this case, what are we solving for? Theta. Okay. So how do you get theta by itself? Very good. Thanks, Graham. Okay. So theta then is equal to the arc length over the radius. So that's going to be 12 meters divided by 35 meters. All right, so what unit will our answer be in? Radians. Very good. Get your calculators out, type that in. It's pretty good. And you? Nice.
This is the first class I've done. True. Like, literally, this is the only class we've done something.
I love it.
At this point, my only classes that I actually have to worry about are English, this. English is a joke.
You're on Chris TV right now. Okay?
Chris TV.
So. All right. Let's see here. Juan, what did you come up with? Yes, sir, with sig figs. Not degrees. What's the unit for the arc length formula? What is that? What's a rad? I'm talking to Juan here. Radian. Very good. Okay. Okay. So we've got we've got 0.34 radians. Okay.
So your picture is not accurate at all.
Whatever. All right. Does that make sense to everybody?
No. I have a question.
Yes.
What about pi?
What about it?
Shouldn't there be a pi formula?
Yeah, pi's already in there. I don't want things in terms of pi.
Oh yeah.
All right. Let's look at the next one. What is the equation for velocity? We're talking about linear velocity here. Raise your hand if you can tell me the equation for that. I just want average velocity. Who remembers from the kinematic section? No, that's force, bro.
Delta x divided by Thomson.
Very good. Okay, velocity equals delta x over delta t.
So this is for average velocity?
Yep.
What is the symbol for it? Let's write average here.
Remember, there is the symbol for average. It was where we just put a straight line over the top of our variable, okay? Okay, so what we're going to do now is relate our equation for linear velocity to circular motion. We're going to try and come up with an equation for angular velocity, all right? Angular velocity has a variable of omega. That's lowercase omega right there. It looks like a W, but it's kind of curving a little bit too much there, okay? And we're going to do the average angular velocity, and that is going to be equal to, all right, what is the counterpart in circular motion to displacement? See, right here we've got linear displacement, delta x. What's angular displacement? Raise your hand if you know that one, okay? All right, Isaac. No. Shivam. Okay. We actually just solved for it a moment ago, okay? Brady?
What's the question?
Just wanted to know the variable for the angular displacement. I want to know what that is, okay? The variable for angular displacement. Sean? Theta. Very good, okay? All right. So in the linear system, we have delta x as displacement, but in the angular system, we have theta. That's our angular displacement. So we're going to put that up here. It's going to be delta theta. All right. Now, in the linear system, we have time. What do you think it is in the angular system? Time, okay?
Oh, because it's that, yeah.
Very good. All right, scalar has no direction, right? Doesn't care what system you're in, translational or rotational, okay? All right, so that then is our equation for the average angular velocity, all right? Let's see if, no, this right here, that's a boxed equation, okay? Boxed equations, remember, are given to you on any quiz or test.
Average velocity.
Yeah. Yep. You bet it. Okay. Now let's see if we can come up with the units for this. Okay. So.
Oh, I know it.
All right. What units do you have for theta, or angular displacement? Radians. And what units do you have for time? Okay, so then the unit for angular velocity is going to be radians per second, okay? Now that's not the only unit, okay? You've got a whole bunch of different units that we can talk about. So let's see here. I could go one full trip around a circle, right? And we call those revolutions, right? So instead of saying things in terms of radians, I could say things in terms of revolutions. And instead of seconds, that's any unit of time that I want to use is fine. What if I wanted to use hours? Okay, I could have revolutions per hour. I could have revolutions per minute if I want to, right? Yes, very good. You should know this as RPM, okay? That's like car stuff there, right? Your little pistons are moving up and down, and they're, cranking the little wheels that turn the axle that turn your tires, okay? The revolutions per minute that you see on your dashboard's tachyometer, that's the RPMs. That's how many times those pistons are going up and down, okay? All right. You could go even further. Theta could be in radians. It could be in revolutions. It could be in degrees, right? So if I want, I could do degrees per second, or I could do degrees per hour, or whatever, okay? So your different units for angular displacement over your different units for time, right? So that would be radians, revolutions, degrees over any unit of time that we want, okay? So understand that you could do that. Now, standard one is going to be radians per second, okay? All right. Okay, so let's see if we can answer this question here. A car tire rotates counterclockwise 3.5 times during a time interval of 0.75 seconds. What is the angular speed of the tire in radians per second? All right. So let's see. Delta theta. What does delta mean? Change. So then that's going to be theta final minus theta initial, right? Okay. So if this thing rotates 3.5 times, what does that mean? How many revolutions did we do just then? Okay. So we could say 3.5 revolutions over 1. And we know that 1 full revolution around the circle is equal to how many radians? 2 pi radians. Okay, cool. So if I did that, that's going to get me my theta in a standard unit in radians, okay? So go ahead, type that in your calculator. Remember, when you have pi, you need to actually use the pi button on your calculator. Don't just type in the digits. All right, Adam, what'd you come up with? No, I need everything. 4858. What? Very good. Okay, now we need to divide that by how long it took, right? Which was, what, 0.75 seconds? Okay. Type that in. Somebody else raise your hand. Isaac, what'd you come up with? Yes, please.
29 radians per second.
Fantastic. 29 radians per second. Okay. Now I want you to convert that to revolutions per minute. When you have it, raise your hand. Should you use your rounded number of radians?
Revolutions per what?
Per minute. I want RPMs I want it again in RPMs. Yep. What'd you get, Garrett?
1700.
No.
Yeah, I got 280.
It's 280. 280 revolutions per minute.